So now let's talk about another way that we can figure out the change in enthalpy of a reaction, and that is using standard heats of formation. So the heat of formation is abbreviated delta H sub F. Heat is synonymous with enthalpy. Remember that enthalpy is just heat flow at constant pressure. So we have the delta H, change in enthalpy, and that little subscript F refers to formation. So the definition of delta H sub F, the heat of formation, is the enthalpy change that's required to produce 1 mole of a compound from its naturally occurring elements in their standard states. Standard states or pure states. The word standard here refers to a temperature of 25 degrees Celsius, which is most lab temperatures. It's also referred to as room temperature. So a temperature of 25 degrees Celsius and a pressure of 1 atmosphere. So that's the atmospheric pressure at sea level. So when we say standard heats of formation, we use this little naught here, this little naught superscript. So whenever you see that little naught superscript, that means that you are referring to standard conditions, a temperature of 25 degrees Celsius and a pressure of 1 atmosphere. So most of the time in this class, we're going to be talking about standard heats of formation at this temperature and this pressure. Let me give you an example. The standard heat of formation of liquid water. The standard heat of formation of liquid water refers to the change in enthalpy required to produce water from its component elements in their pure states. Now, water is made of hydrogen and oxygen, and the pure states of hydrogen and oxygen are diatomic hydrogen and diatomic oxygen. These are the pure states of those elements. So if I combine them in a 2-to-1 ratio to make liquid water, okay, this would be the chemical equation needed to produce 1 mole of liquid water from its component elements, hydrogen and oxygen, in their pure states, their diatomic gaseous states. The heat of formation associated with that is minus 286 kilojoules per mole of water. A few notes about standard heat of formation. Elements in their pure states have a heat of formation of 0. So that means if I'm looking for the heat of formation, say, of the H2 gas molecule, it would be 0. If I'm looking for the heat of formation of O2 gas, that would be 0. So any element in its pure state, so for metals, that would be monoatomic solids. For lots of nonmetals, those are diatomic gases. For certain ones like bromine, it would be diatomic liquid. Elements in their pure states have standard heats of formation of 0. Another really important point is that the heats of formation vary depending on the phase of matter. So you really need to pay attention to whether the compound is a solid, liquid, or a gas, or an aqueous species. Let me give you an example. If I'm looking at liquid water versus gaseous water, liquid water is going to have a standard heat of formation of minus 286 kilojoules per mole versus water vapor. It has a standard heat of formation of minus 242 kilojoules per mole. So there's a pretty substantial difference in their standard enthalpies of formation just from the phase of matter. Okay, so how can we use standard heats of formation to calculate delta H of a reaction? In order to calculate the delta H of a reaction, you can sum up the number of moles of each product times each product's standard enthalpy of formation. Okay, so, and you can look these up in a table. I'll show you where in just a moment. And once you do that for all of the products, you subtract the sum of the number of moles of each reactant times their respective standard enthalpies of formation. So here, the little n value refers to the number of moles, and you get that from the stoichiometric coefficients in the chemical equation. So the number of moles of each product on the left or reactant on the right. So this equation tells us that the enthalpy change of a reaction is found by subtracting the enthalpies of formation of the reactants from the enthalpies of formation of the products. And it's really very easy to do. I'll just do a couple of examples and then you can practice on your own. The first example I would like to do is to calculate the delta H of the reaction for this reaction. We actually did this in a previous lecture using Hess's law, and I just want to kind of use this to show that you can use standard enthalpies of formation or Hess's law to figure out the delta H of a reaction. Here we're calculating delta H naught of a reaction, so of this reaction. So it's at 25 degrees Celsius and 1 atmosphere. And this is nitrogen monoxide plus singlet oxygen giving nitrogen dioxide. And we want to do it using standard enthalpies of formation. So now what you need to do is look up the standard enthalpies of formation of each of the species involved in this reaction. So what you can do as you're doing problems in OWL, as you're working in OWL, there's this references thing at the top, and on references there are these general chemistry tables. So you can kind of click that references references link and then open up the general chemistry tables. And once you open up the general chemistry tables, you can choose the thermodynamic data. Okay, so you can find this right in OWL. Alternatively, you can look at the appendix in your textbook to find thermodynamic data as well. Now, the thermodynamic data that we're interested in here is this column that is the standard enthalpies of formation. And you can see that it's organized by chemical, starting with the first element in the compound. So going from aluminum to barium to beryllium to bromine to cadmium all the way down. So what you would do in an example like this, I think we're looking for nitrogen dioxide gas. So we have a value of 33 kilojoules per mole. We're looking for nitrogen monoxide gas, so we have a value of 90.3 kilojoules per mole, etc. So we can look up those values and then input them into that equation to calculate the delta H naught for this reaction. So when I do that, let's do the products first. I'm gonna just write down the values that I looked up in tables. The delta H naught of formation of nitrogen dioxide gas, that's the product of this reaction, is 33 kilojoules per mole. I'm just rounding to whole numbers for simplicity and speed here. The standard enthalpy of formation for an O gas is equal to 90 kilojoules per mole. Again, I'm just rounding to a whole number. And the standard enthalpy of formation for singlet oxygen gas is 249 kilojoules per mole. So now I can input all of those values into this equation where I'm calculating delta H naught of a reaction by subtracting the sum of the product. So I have, looking at the balanced equation, all of the coefficients here are 1. So I have 1 mole of NO2 times 33 kilojoules per mole. And that is the extent of my products. And I'm going to subtract the reactants. So I have 1 mole of NO times 90 kilojoules per mole plus 1 mole of O times 249 kilojoules per mole. All right, so if I do all of that arithmetic, make sure you obey the order of operations. Here it's not tremendously important. Then I should get about minus 304 kilojoules. Okay, so that's 33 minus 90 is about minus 60 plus 9. Okay, so that gives me minus 304 kilojoules. This might be slightly different from what we calculated for this reaction using Hess's law, but that example couldn't have been at 25 degrees Celsius in this case. So this shows how you can use the standard enthalpies of formation to calculate the delta H naught of a reaction. Let's do another example. Use standard enthalpies of formation to calculate delta H naught for this reaction. 4NH3 gas plus 5O2 gas gives 4NO gas plus 6H2O gases. And again, the species are very important. So you can look up the values of the standard heats of formation in the table. You can use the table in OWL, you can use the table in your book. And these values, I'm going to write them all down in kilojoules per mole of each compound. Okay, so if I'm writing these down in kilojoules per mole, NH3, I'm looking that up, is minus 46 kilojoules per mole. O2 is in its pure state. Any element in its pure state is going to have a standard heat of formation of 0. NO, we actually just used that one, is 90 kilojoules per mole. And water, gaseous water, is minus 242 kilojoules per mole. So I want to put this into that equation to calculate the standard enthalpy for a reaction. I'm going to start with the products. So I have 4 moles of NO times 90 kilojoules per mole. And I'm summing that with the 6 moles of water, gaseous water, times minus 242 kilojoules per mole. Okay, so remember, it's products minus reactants. So that takes care of my products. I'm going to now subtract the same thing for the reactants. I have 4 moles of ammonia, and I'm going to multiply that by minus 46 kilojoules per mole, which is the standard heat of formation for ammonia. And of course, the other one is just going to be 0, right? Because I have 5 moles of O2, but that's 0 kilojoules per mole, so that term reduces to 0. Okay, pardon my handwriting here. That was meant to be kilo. Okay, so that term reduces to 0. So now, if you do all of that arithmetic, you should get a highly exothermic delta H for this reaction. Minus 908 kilojoules is the delta H for this reaction. So as you can see, these problems are very simple. It's just a matter of looking up values in the table and kind of plugging them into that summing up equation and subtracting the standard heats of formation of the reactants from the standard heats of formation of the products. And you use the stoichiometric coefficients to multiply each quantity.